We'll now introduce assemblers and the assembly language. One of the first places where we need a more friendly virtual environment is in our choice of a programming language. The machine language, which is designed from a machine's point of view, is not designed from a person's point of view. And it's also complicated and virtually impossible to understand. So what are the problems with machine language? Glad you asked. Well, I can name a couple. First of all, it uses binary. And, well, let's face it, this is really difficult to understand. There are no natural language words or mathematical symbols or other convenient ways to notate this language. So, I mean, trying to program or read anything in a bunch of ones and zeros, yeah, good luck with that. That's just not going to work. Another problem is that it allows only numeric memory addresses, which I should also mention is in binary. So a programmer isn't going to be able to name an instruction or a piece of data and refer to it by that name. So it's just going to be able to look at those addresses to be able to do any types of instructions. Another problem is it's difficult to change. So, I mean, if we insert or delete an instruction, all the memory addresses following that instruction will also change. So that gets really messy. So, like, for example, let's say we place a new instruction into memory location 503. And that means the instruction previously located in 503 gets shoved into 504. And then all references to address 503 must be updated to point to 504. And guess what? That does not happen automatically. So you would have to go to every single reference of that address and change it. That could be a pain, especially since it's very well possible that there may be hundreds of such references. And then finally, it's just flat out difficult to change the data. So, I mean, if the user wants to store a piece of data in memory, well, that person's going to have to compute the internal binary representation for that data item. And these conversion algorithms are complicated and quite time-consuming. Now, programmers working on the early first-generation computers quickly realized these shortcomings of the machine language. So they developed a new language, which was called assembly language. And this was designed for people as well as computers. Assembly languages created more productive, user-oriented environments, and assemblers were one of the first pieces of system software to be widely used. So this was a lot more user-friendly than machine languages. Was it perfect? No, and we'll get to that later, but it's still a huge step. In fact, when assembly languages first appeared in the early 1950s, they were one of the most important new developments in programming. So important that they were considered an entirely new generation of the language. So you can guess that they became very popular and very widely used in programming. Nowadays, these assembly languages are more properly called low-level programming languages, which simply means that they're closely related to the machine language. And each symbolic assembly language instruction is translated into exactly one binary machine language instruction. Now, this contrasts with some of the languages that we use today, which are called high-level programming languages. These are more user-oriented, they're not machine-specific, and they use both natural languages and mathematical notation in their design. And some of these examples include C++, Java, and Python, and we will be talking about high-level languages much later on in the course. A program that's written in assembly language is called the source program. It uses the features and services provided by the language. However, the process does not understand assembly language instructions in the sense of being able to fetch the code and execute them as we can do with machine level instructions. So that means that the source code has to be translated into a corresponding machine language program. And this program would be called the object program. This translation is carried out by a piece of system software that is called the assembler. Now, for high-level languages, we would use a compiler to translate a high-level language into machine level. But for assembly-level languages, we would use an assembler to translate the source program into the object program. Now, once the object program has been produced, the instructions can then be loaded into memory using a loader, and then we would just execute the instructions as we normally would. We'll now describe a simple yet realistic assembly language that just kind of gives us a better idea of how this works. So what I'm going to be describing here is may not necessarily be an actual assembly language because there are some variations of it, but it's close enough to give you an idea of what assembly language looks like. So let's take a look at the format. So we have something like this, where we have the label, a colon, some opcode, an address field, 2 dashes, and the word comment. So these are kind of placeholders. So what does each part mean? Well, the label is simply an optional name for the instruction's location. And what this does, it allows us to make the code easier to read and easier to maintain. It also helps us where if we need to jump to a particular instruction, instead of having to jump to a specific memory address, we can jump to the label instead. That way, if we add and change stuff with the instructions, we don't have to change every reference to a memory address because we don't have to deal with that anymore. We can use the label instead. The opcode is the symbolic name that corresponds to the instruction. So instead of needing to know the actual binary code for a particular operation, we can just use a symbolic name for the opcode instead. And then the address field is just a symbolic address. And we can use letters, we can use words instead of having to deal with the numbers for the address. And then the dash comment, this part is actually ignored by the assembler, but it does help out the user. These are additional instructions, or I shouldn't say instructions, but they're kind of more of like text that people can read so they kind of have an idea of what this instruction is doing, but it's completely ignored by the assembler. So let's take a look at least a couple of examples. So we might have something like next step colon load X. And what that is saying is we're going to put X into register R. So load X is the instruction. Next step is the label for it. And then the 2 dashes means that everything to the right of that is a comment. So the fact that we say put X into register R, we can put that in our code, but our assembler will not read it. Another example may be the instruction jump next step. And then we have a comment here that says go to instruction at label next step. So this instruction would actually say go to the line where it's labeled next step. We can actually have the assembler convert signed and unsigned values into binary by using a special type of assembly language opcode. This opcode is what we call a pseudo-op. Now, a pseudo-op does not generate any machine language instructions like other operation codes, but instead it invokes a service on the assembler. One of these types of assemblers, or one of these services I should say, is generating data in the proper binary representation for the system. There are typically assembly language pseudo-ops to generate integer, character, and if the hardware supports it, real data values. So in our sample language, we'll limit ourselves to one data generation pseudo-op, which we're going to call .data. And this would build signed integers. So this pseudo-op will convert the signed decimal integer in the address field to the proper binary representation. So for example, we might have something like 5 :.data plus 5. So what this does, it tells the assembler to generate the binary representation for the integer plus 5, put it into memory, and then make the label 5 equivalent to the address of that cell. Let me give you another example. We might have something like -7 :.data minus 7. So this is going to tell the assembler to generate the binary representation for -7, store that in memory, and then use the label -7 to represent the address of that data. So the whole point here is now we can use these labels to return to the values instead of the actual memory addresses. So using these pseudo-ops, we now can have several other instructions in our assembly language. So I'll give you just a couple of examples. So we could say something like load 5. And from our previous slide, we can say that this is just loading the value of 5 into register R. Or we can do something like add -7. So using the -7 that we created in the last slide, this would add -7 to the current contents of register R. Now we could have some other pseudo-ops as well, because a second service that's provided by these pseudo-ops would be program construction. So we can have operations that mark the beginning and the end of an assembly language program. So .begin in this case would specify the beginning of a program, and then .end would specify the end of the program. But that does not necessarily mean that it terminates. Remember, we still need the halt instruction in order to terminate the program. Because remember, pseudo ops are not translated into machine instruction. They're just to help us understand what's going on, or maybe to be able to provide some additional services that can be provided by the assembler.